So, welcome to class on the 14th of April. We've been doing this way for about a month, getting a little stir crazy and wondering how much longer are we going to do this? If Dr. Fauci has his way, it might go on for months, and maybe the fall semester won't even be face to face. But we'll see. The president's got other ideas, I think. Uh, I would take the advice of an essayist, Lance Morrow. I read his essay, and he says, what you have to do is you can't lie around in your pajamas all day. You got to have a routine that's more like your normal life. So I wake up at 3 a.m. I know you're not going to get up at 3 a.m. Sleep until 4 a.m. Then you have to do some exercise, have coffee, dress in your normal clothes, shave, do all those primping kind of things. Then go outside and do things. Walks. I walk about 4 miles a day. Work in my garden. Then indoor, when you're done with that sort of thing, what do? I watch Red Zone. If you don't know what Red Zone is, then you won't want any part of it. And then I think I'm the only person in America who has not watched Tiger King. I mean, even at the president's press conferences, I hear talk about Joe Exotic. I don't know who this guy is. So I think I got to break down and just if I want to keep up with my fellow Americans, I've watched Tiger King. Now, topic for today is we're beginning data analysis. We're going to do univariate analysis, but let's put that in a context. We see that there's a cycle of research. We've been using that to organize our semesters. So our semesters work. We start out with a hypothesis we want to test, right? We go to research design, a plan. How can I gather empirical information to test this hypothesis? We carry out that plan, we do measurement, and measurement produces data. Now, data in its raw form won't help us really understand the hypothesis we're testing. What we have to do is we have to do data analysis. We have to put the data in a form that will allow us to make determinations about the topic we're interested in. Now, data analysis techniques, this is what rely on the mathematicians. The branch of mathematics called statistics is what we're into. And statistical techniques can be divided up several ways. A way I'd like to divide them up now is that we have statistical techniques that we use when we just have one variable we're interested in. We want to describe that variable. They're called univariate techniques. We're going to spend some time today on univariate techniques. And you should think in your mind, if you have one variable and you want to describe to another person what the data are like for that variable, say you're a data analysis person working in a polling firm, and an ex-Republican vice president, Dan Quayle, wants to know, should I throw my head in the ring? Should I run for president, right? When Trump's gone from the scene. First thing you'd want to do is a poll. Probably 1,200 people on the telephone. You do that poll, and then Mr. Quayle calls and he wants to know how was the poll? And you take, say, a question like the thermometer scale. On a thermometer scale, from 0 is you're cold towards somebody, 100 is you're hot. He'll want to know, how did I do on the thermometer scale? You could pick up the 1,200 questionnaires and say, here's a 50, here's a 20, here's an 80, and go through. Well, that won't do any good, will it? You got to analyze that thermometer score into form that will convey to a person exactly what's in that variable. Think in your mind, what could you tell Mr. Quayle? Well, first of all, you could tell him, what is the typical case like? That is, what is the mean? That is called a measure of central tendency. What is that center of gravity like for that variable? The next piece of information you could tell Mr. Quayle is how spread out are the cases from the mean? Are many of them very close to the mean, or are they all spread out? Those are called measures of dispersion. And we're going to go into measures of central tendency and measures of dispersion in univariate analysis today. But I want to talk about how you can move up to more complex levels of doing an analysis, where you only take one variable. Now let's take two variables and lay them side by side. What questions could a statistician answer about them? of these two variables together? Well, the first question of interest is this. These two variables, they're taken, you have a sample, there's a population out there. We want to know, are there grounds to think these two variables are related in the population? Uh, the statistical techniques used to answer that question, are these two variables related in the population? Those statistical techniques are called test of statistical significance. You've probably heard that term. Such and such is statistically significant. It has a special meaning to methodologists, meaning something statistically significant. Are there grounds that a rational person could say these two variables are related out in the population? Now, once you do a test of statistical significance, many times you'll find out, yeah, they are related. They are related out in the population. Then the analysis can go further. Then we want to know how strong is the relationship and in what direction does it go. There's a whole group of techniques called measures of association that we'll look at in our final tapes, our final videos of the semester. And they answer this question, how strong is the relationship between these two variables? And is there a directionality to it? And in what direction does it go? Uh, Finally, so we went from one variable to two variables. Now we can take many variables together called multivariate analysis. This is what we do when we do mathematical modeling. Uh, most of the social science world is multivariate in nature. So multivariate analysis comes closest to kind of capturing what's going on in the world. Uh, and Multivariate analysis might be done by the CBO, the Congressional Budget Office. Anybody fans of the CBO? They do publications all the time. They do multivariate kind of analysis to help Congress understand how much does this program cost now? Uh, how much will we spend this year? What will the deficit be like? So I imagine the CBO is busy right now trying to figure out exactly what the national debt's going to be a year from now. Think of that in your mind. The national debt is now at $23 trillion. We add to the national debt when we borrow money in order because our spending is more than we take in taxes in a year. So we've accumulated $23 trillion. What do you think is going to happen after this year? Congress just passed a $2 trillion bill to help people get through these hard times with the COVID-19. I hear they have another one in cooking away, embryonic, another $2 trillion. So what if Congress spends $4 trillion above the $4 trillion we usually spend? Plus, well, this year in taxes, we're probably going to take in less in taxes. So many people aren't working, they're going to pay less out in taxes. So we might add $4.5 trillion or something like that to the economy. Well, all we want to know the exact, with some exactitude, what this is going to be. This is what multivariate analysis is like. So you have this dependent variable, this amount we're going to borrow this year, and they'll plug into it how much do we think we'll take into taxes, and that'll be determined by, well, how many people will be working, in what percent do they pay in taxes, and then it'll have a spending part of this multivariate modeling. How much are we going to spend? And then we'll get a final bottom line about this sort of thing. This is what multivariate analysis is like. We're going to do univariate analysis and bivariate analysis, and what we won't get into multivariate analysis, but I'm sure you go to graduate school, you do more methodology courses, you'll get into that sort of thing. Now, let's do remaining time on our tape. Let's do univariate analysis. Remember, we want to take one variable and we want to look at that variable. And we want to convey to people, what is the typical case like? What is the central tendency? And we want to convey to them, what is the dispersion? How spread out are the cases from the central tendency? The mathematicians have worked out techniques for us, and they'll say the appropriate technique to be used in univariate analysis will depend upon the level of measurement of your variables. And remember, we talked about the 3 levels of measurement. I'll put up a chart now. I'll give you a chart. I'll take a picture of you. Send me an email to remind me. I'll take a picture of this chart and send it off to you so you can see it better. What this chart does is it builds on what we've been doing before. We started out with what are the kinds of concepts you have. And the lowest level of concepts is called the classification concepts. Then a couple classes ago, we talked about level of measurement. Well, the level of measurement for a classification concept is called a nominal or a categorical level of measurement. Now, I've added what is the measure of central tendency that it's appropriate for this level of measurement? Well, it's the mode when you're at this, when you have nominal level data. And then what is the appropriate statistical technique for measuring how dispersed are all the cases from this central tendency? And we're going to look at something called the variation ratio here at this lower level of measurement. Let's get a little more complex. Let's go up to the comparison concept. Remember, a comparison concept is you measure along a scale of some kind. That yields data that the methodologist called the ordinal level of measurement. There's a different measure of central tendency at this ordinal level of measurement. It's called the median. We're going to talk about the median. And then finally, when you want to say how spread out are the cases on one of these comparison concepts, there's a technique called the decile range that we're going to look at. Now, let's go up to the highest level of measurement. Highest level of measurement, we have a quantification variable, right? It yields, for a level of measurement, it yields data at the interval ratio level of measurement, right? And if we want to look at what the central tendency is like, what is the typical case? We have a central tendency technique called the mean that you've used all the time, put together by the statisticians. And finally, when we want to look at how spread out are the cases, what is the dispersion when we're at this quantification interval ratio level of measurement, we have a technique called the standard deviation that you've heard about. Maybe you've not calculated, but we'll talk about that. Now, let's go on and let's look now. Let's go through the parts of that chart now, starting with the measure of central tendency, the mode. The definition of the mode is just this. The mode is you have this classification concept and you have people or cases placed in the various categories. The mode is the category that occurs most frequently. That's the measure of central tendency. Not very sophisticated, but we're at this lower level of measurement. We're at this nominal level of measurement. There's not much information contained in there. So all you can do to convey to somebody what the typical case is like is tell them what category occurs most frequently. Take an example. We have religion, a classification concept measured at the nominal level of measurement. And let's say we have 100 people. And there are 30 Roman Catholics, 67 Protestants, 2 Jews, and 1 with another religion. Well, the mode is the category that occurs most frequently. Since there are 67 Protestants, there are more Protestants than any of the other categories, the mode of that variable is Protestant. It's not the 67, it's the Protestant. People mix up that all the time and think the 67 is the frequency of the modal category, but the mode is that category, Protestant. So that's what you do when you do a measure of central tendency for this nominal level of measurement. Let's go down and talk about an ordinal level of measurement. The proper measure of central tendency is the median. Simple definition of the median. You're at the ordinal level of measurement. The cases exist along a scale of some kind with a greater or lesser amount of something. The median, how you convey to people what the central tendency is like, you say, what is the value of the case that's right at the middle of this spread, where 50% of the people are less or 50% of the people are more? That's the median. And it's properly used at this ordinal level of measurement, but sometimes we use the median when we're at the quantification level, the interval ratio level of measurement. So the median is used to convey to people in America what is the typical family's income like, and we'll give the median family income rather than the mean. We'll see the problem with the mean is outliers, cases that are way out, pull the mean way off so you don't get a good feel for where the middle case is like. But the median is very useful in this respect, and so we use the median to convey that sort of thing. Now, finally, let's go up to the interval ratio level of measurement, right? We're talking about measures of central tendency here, and the mean is something you've been calculating all along. gives you what the typical case is like, what the central tendency is like for the interval ratio level of measurement. So mean might be you have 10 quizzes going from 0 to 100 in a course. You've been calculating the mean. You just add up the total amount of points you have and divide by 10, and you get the mean. And that gives you an idea of what the kind of typical case is like. Now, these are the measures of central tendency. Now we'll move on to the chart to what the measures of dispersion are. That is, these measures of dispersion tell us how spread out our cases from that mean. And I put on this chart, we've got the variation ratio. We're going to look at that. And we got the decile range, and we got the standard deviation, which is the measure of, these are all the measures of dispersion. Now let's start with the variation ratio. By definition, it's the appropriate measure of dispersion when we're at that nominal level of measurement. And here's what the variation ratio is. The variation ratio is equal to 1 minus, and in parens, the frequency in the modal category over n, where F mode is the frequency in the modal category. How many cases occur in the modal category? And n is the number of total cases in your study here. So if we take an example, take that example of religion that we talked about. I said that in our religion example, we have 100 people. There were 30 Roman Catholics, 67 Protestants, 2 Jews, and 1 other. Well, the first thing before we plug the numbers into this equation here is we got to know the frequency of the modal category. Well, the mode is Protestant, and 67 is the frequency in the modal category. So we plug in the numbers, and there's 100 cases, so it's going to become 1 minus 67 over 100, which comes out the variation ratio is 0.33. Now, how do you interpret a variation ratio? Well, it ranges from 0 to 1. Where do you get the variation ratio equal to 0? Think of that. Look at this formula here. How do you make this 0? Well, imagine that you did your study of religion and you polled people as they walked out of a Muslim synagogue. You got 100 people and you got all kinds of questions you ask them. When you look at religion, all 100 were Muslims that walked out. So imagine, Muslim is going to be the mode. 100 is going to be the frequency in the modal category. So you get 1 minus, and in parens you have 100 over 100, which is 1. 1 minus 1 is 0. That's going to be a variation ratio is 0. Doesn't that make sense? There is no dispersion in a variable like that where everybody is in the same category. And so the variation ratio is 0. Now, how do you get this bigger? How do you get this number bigger? Well, rather than concentrating people in one category, you spread them out as much as you can, right? That's how you get it bigger. So in the religion example, if we had 34 Protestants, 33 Catholics, 33 Jews, like that, if that was your example, well, then your mode is Protestant, and you have 33 in that Protestant category. So 1 minus 34 over 100 is 0.66, meaning the variation ratio moves from 0, where you don't have any variation at all, and as you spread the cases out, it moves closer and closer to 1. Doesn't quite get to 1. You can get the variation ratio higher when you have many categories to your variable there. And that's how the variation ratio works. Now, let's move up to the comparison data. Ordinal level of measurement. Let's look at the decile range. This is a measurement of dispersion for this ordinal level of measurement, and it's pretty straightforward. The decile range is R sub h minus R sub L, where R sub h is the rank of the 90th percentile case. R sub L is the rank of the 10th percentile case. So imagine you're at this comparison concept at the ordinal level of measurement. You can rank the cases along a spectrum of some kind. You rank them from the lowest to highest. You find out what rank or what is the score for the 10th percentile case, RL, and then you take the 90th percentile, RH. What is that rank? And then what you've done is chop off the top 10% and the lower 10%. That middle 80%, you want to know how big is the range there. So, example that I would present to you in class is years of schooling that people might have, and you rank them all the way from 0 all the way up to I have 16 in here. And if we find out that R sub L, the lowest 10%, 9 years of schooling is that R sub L, and that we look at the R sub H, the 90th percentile, and that is 15 years of schooling. That means 15 minus 9 is 6 years. 6 years captures that 80% that's in the middle, and that's how we express the dispersion when we're at an ordinal level of measurement. Finally, let's look up here at the area that the statisticians really love. A lot of information contained up here when we have a quantification concept measured at the interval ratio level of measurement. And we have the standard deviation, which is the measure of dispersion for this interval ratio level of measurement. Well, here's the formula. S has been taken by the statisticians to be the standardized variable letter that represents the standard deviation, and S is going to equal to everything is within the square root sign. And inside we have, this is the summation of x sub I going from 1 to n. Let's say you have 4 test scores. Well, x sub 1 is your first test score, x sub 2, x sub 3. Now what this is saying is you take x sub 1 and subtract the mean from it and square that. Then you go to x sub 2, your second score there. You take the mean from that and square that and add it to the pile. Then you do it for the third and the fourth. So you sum all that, and then you divide it. You divide it by n1 minus 1, and then you take the square root of that. Now, that's kind of complicated to follow and get a feel for it. So wouldn't you know that the statisticians have worked out for us a way to get a grip on how to understand the standard deviation. Here's what they've come up with. They've come up with something called the empirical rule. And I'll give you an example. Here we have a chart of the height of people in the United States. And we have the number of people over here and their height. And it would be a standard bell curve. See the bell curve in here. The mean we have is 68 inches. That is the mean of height for people. And the standard deviation is 2 inches. So what we do is we put the chart down here. Here's the mean of 68 inches. What we do is we add 1 standard deviation, that's 70 inches, and then we subtract 1 standard deviation, that's 66. Now, that means in the interval between 66 and 70 that we captured 2/3 of the cases within the interval that marks +1 standard deviation and -1 standard deviation. Then we go further and we take 2 standard deviations. We add 2 standard deviations, which would put us here at 72, and we subtract 2 standard deviations. We're at 64. So between 64 and 72, we've captured 95% of the cases. That empirical rule gives you an idea when you know the mean and you know the standard deviation, you know someone's score, you know where they are in this. A thing to look at this kind of is that you've got 95% of the cases within the interval -1 standard deviation, -2 standard deviations, and +2 standard deviations. That means 5% are not captured within 2. 2.5% are out here and 2.5% are out here. That gives you an idea to try to understand how far off are people, how different are they than other people. This was used when I was reading an article about intelligence in the United States. And they said that the average intelligence in the United States measured by IQ is 100, right? And the standard deviation is 15. So they were saying that the average, for the average Harvard freshman, their IQ was 135. So you know just how high that is. If the mean IQ is 100 and the standard deviation is 15. That means if you go up 2 standard deviations at 130, there's only 2.5% in that tail up there. So the typical average Harvard student is going to be in the top 2% in intelligence in the United States. This has important implications for the direction that American society is moving. We can talk about it when we have more time, but that's what I want to give you on univariate analysis. What you should do is go to Blackboard and go to the discussion section, and I want to hear your comments and questions about this. And if I don't remember, tell me to take pictures of those charts, and I can email you those charts so that you can make some sense out of the things that I'm saying today. Thank you, and I'll see you on Thursday.